Hey everyone, let's talk a little bit about graphs now. So what is a graph data structure? So the data structure that you're seeing here, okay, it's a network of nodes. It is actually a graph, okay. So it's a network like data structure, you can say. And what are the elements we have in this particular network? We can see there is a collection of nodes. 5 is a node, 4 is a node, 25 is a node, and there is a collection of edges. Okay, so we have a network of vertices, or you can call them as nodes, and we have some connections between them, so we call these connections as a edge. Okay, so we also have edges here. Okay, so now you may ask, okay, why do we need such kind of a network? So the answer is very simple. Real life data can have network like properties in between them. Okay, if I talk about a group of people on Facebook, so many of them are connected, many of them are not connected. So we have connections, and each person can be connected to multiple people. They may also have mutual friends, they may also form cycles, they may not form cycles. Two uh, two groups of people may be connected, they might not be connected. Okay, so we will see a lot of real life applications talk about, let's say these are the cities and these are the roads connecting them. They can also be represented using a graph. So on the very basic terms, what we will have vertices, and we will also have edges. So now these edges can be of the different types. There could be directional edges which move only in one direction from A to B. Let's say there is an edge, or there could be bidirectional edges. That means from A to B there is an edge, and there could be an edge from B to A as well. Okay, these edges can have also weights. Maybe going from A to B takes, let's say, 10 minutes, and maybe coming back from B to A also takes 10 minutes. But maybe these two roads are different, and while coming from B to A there is a, let's say, traffic jam in between, so maybe this may take 20 minutes. So these weights can be same, or these weights can be different. So depending upon whether the edges have weights or not, we divide the graphs into two categories. One is called as a weighted graph, and another is called as a unweighted graph. Okay, so the graph in this particular figure is a unweighted graph. Similarly, we can also have directed graph in which edges have certain directions. So we can also classify graphs as directed graphs, or if they don't have any particular direction, that means the edges are bidirectional, we can call such a graph as undirected graph. Okay, so directed versus undirected, weighted versus unweighted. Okay, so that's basic few terms that we will see frequently in a graph. Now if we want to solve a graph problem, we need this data structure in memory. Okay, we need to store this data structure. Okay, we need to store this data structure in memory. So when we talk about memory, we generally talk about RAM. Okay, so these data structures, when the program executes, they are stored inside the RAM memory, and we want a mechanism using which we can store a graph. So there are generally 4 common ways in which you can store a graph. One is adjacency list. This we will use a lot in this course, and we will see the details. Then another is adjacency matrix. Then we have edge list, and we will have 2D matrix, that is sometimes called as a implicit graph as well. So let us go through this one by one. So what is a adjacency list? So it's a way in which what we do, we make a list of neighbors for each node. Okay, so let's say we have 0, and what are the neighbors of 0? So we have 1, 2 and 3. So we will create a list of neighbors and we will store it in front of 0. Okay, now you may ask, okay, where is this 0 stored? So maybe this whole row is a array, or it is a list. Similarly, we will have a list for 1. So what are the neighbors of 1? So 1 has neighbors 0 and 2. So this row is another list. Okay, so this is list of 1, this is list of 0. Okay, this is list of 0. And maybe talk about 2. 2 has neighbors 0 and 1. So this is another list. What about 3? 3 has only one neighbor, that is 0. So this is list of 2, or let's say list of 3. This is list of 2. Okay, so we, what I'm trying to say is, this whole data structure can be represented as a list of lists. Okay, or it could be a array of lists, or it could be a vector of lists. Okay, or it could be a vector of vector. Okay, or it could be a hash map. Okay, it could be a hash map, like we have unordered map in C++. So it could be an unordered map of the type integer followed by a list. Okay, so this list can be of integers, or it could be of a different type as well. So we will see these implementations later on in this course, but that is the idea of adjacency list. Now what is the advantage of using a adjacency list? The advantage is, in many of the graph algorithms, what you will observe is, doing this operation is a requirement. So what is the operation? Given any node, we want to find the neighbors of that particular node. Okay, so given a node, what are the neighbors of that node? So you can directly get those neighbors from a adjacency list. Okay, you can go to this row in order one time, and let's say this has x number of neighbors. Then in order of x, you can iterate over the neighbors of that particular node. So this is a very frequent operation in algorithms like BFS, DFS. We will see adjacency list comes very handy in implementing those algorithms. So that is the advantage of using a adjacency list. Secondly, it is space efficient. It does not occupy, it doesn't waste a lot of memory. Okay, so this much memory is at least needed to store a graph. So that is why it's quite space efficient. Let's talk about another representation that is known as adjacency matrix. Now if you look carefully, what we have a, if we have n nodes, or let's say if we have v nodes, we are using order of v square space to create a matrix, and this basically tells us whether there is a connection between any two pair of nodes or not. For example, I want to check if there is an edge between 2 to 1. So what I will do, I will check 2 comma 1, does it have an edge, or I can check 1 comma 2. So yes, there is an edge between there is an edge from 1 to 2, and there is an edge from 2 to 1 as well. Okay, so we mark that position as 1, and all other locations where we don't have an edge, for example between 3 and 2, we don't have an edge here, so this is marked as 0. Or maybe these edges have weights, maybe this edge has a weight 2, so we will put this weight as 2. Okay, so using adjacency matrix, you can represent both directed and undirected graphs, also weighted and unweighted graphs. The disadvantage of using adjacency matrix is, so there are two disadvantages. One is it is going to waste more space. For example, if you have, let's say, 10 per 6 nodes, then the adjacency list will have a linear space complexity, linear in terms of vertices and edges, but this would end up getting order of v square. That means a huge matrix will be there inside the RAM, and that much memory might not be available. So disadvantage is too much of memory is needed. And second is in order to get the neighbors of a particular node, okay, let's say the 3 has only one neighbor, but in order to see how many neighbors this has, we have to spend order of v time iterating over this entire row to check what are the neighbors of 3. Okay, but in case of a adjacency list, we can directly get, okay, there is only one node that is the neighbor of 3. So this is quite inefficient when it comes to finding neighbors of a given node. Let's talk about another operation, that is edge list. So in some algorithms, particularly when you have to do some kind of sorting based upon edge weights. So one such algorithm is like in minimum spanning tree. What we do, we may need to do the sorting of these edges based upon the weights. So what data structure comes handy is, we don't want to find the neighbors, but we want to sort the edges, let's say based upon their weights. So we will create a edge list. Okay, so with every edge list we will also store what is the weight. We will create a edge list. Okay, edge weights, so to do some kind of list. So in some algorithms, particularly when you have to do some kind of sorting based upon edge weights. So one such algorithm is like in minimum spanning tree. What we do, we may need to do the sorting of these edges based upon the weights. So what data structure comes handy is, we don't want to find the neighbors, but we want to sort the edges, let's say based upon their weights. So we will create a edge list. Okay, so with every edge list we will also store what is the weight w1, w2, w3, w4, and then we can say, okay, let us try to sort this edge list based upon the weights. In that case, we will make use of this data structure. So it is nothing but it is list of pairs, or there can be triplets also, where in each triplet we are storing the weight, the source, and the destination of the edge. Okay, so let's say there is an edge from A to B and it has a weight 6. So this is how we are going to store this information in the form of a list of triplets. So this is one common representation that you will definitely encounter. So let's talk about what are implicit graphs. So in many problems you would be given, okay, there is a 2D maze kind of a data structure, and maybe you're standing at this particular point and you can move in all 4 directions, top, right, up and down, and maybe tell me in how many ways I can reach this point, or maybe what is the shortest route to reach this particular point. So in this case you're not given the nodes, but you can assume that each node is connected with 4 neighbors. Okay, what we do, we don't create any other data structure. We already know the relationship between the nodes. Okay, so if this coordinate is I comma j, we know that if we want to go to the representation that you will definitely encounter. So let's talk about what are implicit graphs. So in many problems you would be given, okay, there is a 2D maze kind of a data structure, and maybe you're standing at this particular point and you can move in all 4 directions, top, right, up and down, and maybe tell me in how many ways I can reach this point, or maybe what is the shortest route to reach this particular point. So in this case you're not given the nodes, but you can assume that each node is connected with 4 neighbors. Okay, so what we do, we don't create any other data structure. We already know the relationship between the nodes. Okay, so if this coordinate is I comma j, we know that if we want to go to the neighbor, simply do I comma j minus 1, or simply do I comma j plus 1, or you can do I minus 1 comma j, or you can do I plus 1 comma j. So we already know what are the 4 neighbors of a given cell. So these kind of applications you will also see in flood fill. So this is a common technique, a common graph algorithm also used as an application in graphic softwares like MS Paint or Photoshop. So where we want to fill a particular color in the entire region. So we will see the pixels are having four-way connectivity. Okay. In some problems, you might be given that the connectivity is eight-way connectivity. Okay. So eight-way connectivity basically means diagonals are also included. So we can move in 8 directions from a given cell. So this connectivity in an implicit graph can be four-way connectivity or eight-way connectivity. It would be given inside a problem statement. Okay. So don't worry if you're confused. We will go through examples for each of these representations as we solve more and more problems in this course. So that's all for this lecture. Thank you for joining. Hi everyone, in this video we'll discuss graphs and we will talk about what makes graphs such an important data structure for interviews for a lot of product companies. So let us discuss 10 cool applications of graphs. So graph is a set of nodes connected through some edges. Each node represents some information and each edge represents a relationship between two nodes. Okay, so let us discuss what cool applications the companies have built using graphs and what makes it so popular. Number one is shortest paths. So applications like Uber, Ola, Google Maps, they all use the graph algorithms to calculate the shortest distance from one location to another. Okay. And the next application is about social networks. In social networks like Facebook, Instagram, LinkedIn, you have millions of people. They are connected with each other. So we can represent these relationship using a graph kind of a data structure. And using this data structure, we can come up with algorithms to find mutual friends, to show recommended posts, or to show friend suggestions, and so on. Okay. So these are used widely in social networks. Another is in finding the shortest cyclic route. Okay, so one application we have already discussed in navigating from one place to another. In shortest cyclic route, we have a different kind of a graph algorithm using which if you start from one location and you want to come back to the same location by covering, let's say, all the points. For example, a school van wants to drop all the children and come back to school, or a Amazon delivery van wants to start from the warehouse and come back to the same location by delivering all the parcels. Okay, so we want to come up with a route that minimizes the total cost. Okay, so that we can optimize our route and save our costs. So this can be done using a graph algorithm. Next is in resolving dependencies. So when you work on servers, you have to install different modules, different libraries. So all of these modules also have dependencies. For example, a module C is dependent upon X, B is dependent upon C, A is dependent upon X, or B is dependent upon A. So you can have a complex structure and you want to find out what is the right order in which these dependencies should be resolved so that there is a no conflict. Okay, so we can use a graph algorithm to give us the right order. and such graphs are called as directed acyclic graphs, DAG in short. Okay. Next is in routing algorithms. The entire world, the internet is nothing but a network of data packets flowing from one continent to another continent, and these data packets flow through routers. So in order to find out the most optimum path for data packet to flow, we use routing algorithms, which also use graph based techniques to find out what is the most optimum path, or what is the path with the least network congestion. So we definitely use graphs there. Next is in machine learning. So in machine learning, when we use deep learning networks, so they also kind of construct a computation graph to optimize the calculations that are being done in order to save processing time, in order to avoid redundant work. So a lot of computations are done by optimizing a graph like data structure called as a computation graph. In computer vision, we also use graphs to, so some of the algorithms, for example, in image segmentation. Image segmentation is finding out where an object is and its pixel wise segmentation, you can say, okay, or the exact boundary of that object. We can use graph based algorithms. And also in algorithms like flood fill in Photoshop or in Paint, you have this paint bucket tool in which you drop a red color and it will fill out to the entire region till you don't hit a boundary. It's a very simple algorithm that can be used to build a paint bucket tool kind of a stuff. In web crawlers, okay, so what happens is, a web crawler is something that traverses the entire web. Okay, so what we can do, let's say we visit a website, we get some links. Using those links, we can go to new links. From those links, we can get more new links, okay, because each web page contains multiple links. So we can traverse the entire web in a breadth first manner. Okay, so this is again a cool application of a graph in order to build a web crawler. Next is in physics and chemistry. I'm not a uh, physics and chemistry guy, but yeah, graph algorithms are used to model molecular structure and process them and do some research also. And one very important application in software industry is, there is a graph database. Okay, an example of a graph database is Neo4j. So it is used in different kind of applications, like in recommendation engines, fraud detection, and AI based application, where it is important to represent the data in the form of a graph. It's different from SQL or no SQL based data structures. The data is modeled as a graph data structure, so it's also used there. And there are a lot more applications in linguistics, social science, biology, neuroscience. Okay, you can see the brain is a network of neurons, and information transfers from one neuron to another. So scientists use graphs to model or mimic the structures in the brain also. So there are a lot other applications as well. So that's all for this video. I hope you are. Hi everyone, so in this example, or mimic the structure. Example, we will see how we can create adjacency list representation for a given graph. Okay, so for most of the problems we are going to define graph as a class from which we can create an object. Okay, and although it is not necessary, but I would recommend using this way because it helps us to make data sharing easy between different functions of the class. Okay, so let us see how we can create a adjacency list. So first thing that we are going to do, is we are going to have this data structure. Okay, so the way we can create adjacency list is for example, we want to store what nodes are connected with 0. So we have 1 and we have 4. What nodes are connected with 1? We have 0 and we have 2. What are connected with 2? We have 3 and we have 1. So this kind of representation we want to make for all the nodes till 5. 5 is connected with 4 and it is also connected with 3. We are talking about the direct neighbors. Okay, so 5 has 2 direct neighbors, 3 and 4. So how do we create this kind of a data structure? So one way is we can create an array of lists. We can create a array of lists. So what is a list here? So we have this entire row. This is a list, this is a list, this is a list, and we can say, okay, we have this array of lists. This whole thing is nothing but a array of list. 0th element of the array is mapped with the list. First element of the array is mapped with the list, and so on. Okay, so let us see how we can create an array of size v, and we can put all this data inside this array of lists. So for that, what I'm going to do, I'm going to include the list stl, that is a double linked list from the C++ standard template library. And when this class is initialized, okay, when this class is initialized, what we will do, we will say, okay, we have list of integers star l. So this is not a list object, this is actually a pointer to an array of lists. So we are creating a pointer to an array of lists. Pointer to an array of lists. So if you want to create a list, okay, if you want to actually what we will do, we will say, okay, we have list of integers star l. So this is not a list object, this is actually a pointer to an array of lists. So we are creating a pointer to an array of lists. Pointer to an array of lists. So if you want to create a list, okay, if you want to actually I'm going to do dynamic allocation because the size of the array is not known in the beginning. Okay, so we are going to use dynamic memory allocation in this case. So I will tell you how do we allocate this array. So what we will do, we will create a graph constructor where we will take in how many vertices this graph is going to have. So we can say v equals to v, and we also need to declare how many vertices this graph will have, and we can say l is going to be new list int v. So now you can see this is how you can create an array of linked lists. So if you want to create a new linked list, you can simply say l equals to new list of integers. Okay, So this creates a single linked list, but you want to create v number of linked lists. So you can say this is an array which contains v linked lists, and the pointer will be of the type list int star l, because it's a dynamic memory allocation. So this is the exact statement that we are executing. So we have defined l here, and l is now pointing to a valid memory, and we have done the declaration here. Okay, so now what we have an array of size v. Each element of the array is a linked list. Okay, so this is l0, this is l1, this is l2, and so on. Okay, each element is a linked list. So we can start a linked list from each position. So that is what it is. So how do we add an edge now? So someone tells us there is a edge between a node I and a node j. Okay, and let us assume that it is a bidirectional edge, or it's a undirected graph. So we can set this boolean property to false if it is a directed graph. So if there is an edge from, let's say, 0 to 1, so what we can do in our linked list, for the 0th position we can say push back a node 1, and for the first position we can say, okay, push back a node 0. Okay, so in the first, or maybe from 1 to 2 there is a edge, so we can say, okay, in 1 you push back 2, and in 2 you push back 1. Okay, and if it is a directed graph, there is an edge from 2 to 3, so you can simply say in 2 you put a node 3, and that's it. Okay, so this is how our adjacency list will be created. So let us do this stuff now. So these are not exactly nodes. So we have these objects. So this is L0, this entire object is L0, this object is L1, this object is L2. Okay, so let's see what we can do. So we can say L of I dot pushback j, and if it is a undirected graph, the reverse will be true also. L of j dot pushback I. So this adds the edge, and now in the main what we can do, we can say, okay, we want to create a graph. So let's create a graph with 6 number of nodes, and we can add an edge. We can say, okay, there is an edge from 0 to 1, and similarly we can add more number of edges. Okay, and maybe we can write a function to print our adjacency list that shows how does this adjacency list look like. So let us write a function to print adjacency list. So void print adjacency list. What we can do, let's see. So what we can do, we can iterate over all the rows. So we have v number of rows. Okay, so for int I equals to 0, I less than v, I plus plus, and we can iterate over all the elements in each row. Okay, so every element of ith linked list, and we can print it. Firstly, we can print in which row we are. So we can print I, and followed by we can print every element. So for auto, whatever is the node that is there in L of I, we can say cout node. So this node will be an integer. So either you can use int or you can use auto. So auto automatically determines the data type based upon the data that is there on the right hand side. So this is a for each loop. So we are picking up every node that is in the ith row and we are printing it, and after every row we can just print endl. So that's it. Let's save and build our code. Okay, so we are able to build it. Now let's try to run this code. So this is the graph that I have, and let us see by running the code if we get the adjacency list. So it says 0 is connected with 1 and 4, which is fine. 4 is connected with 0, 3 and 5, 0, 3 and 5, which is fine. 5 is connected with 4, 3, which is also fine. Similarly, you can verify that this adjacency list is a correct representation. So that's all, and see you guys in the next video. Hi everyone, so let us look at another way of creating the graph data structure. So now we have a collection of nodes. Each node is not an integer, each node is a maybe something complex, but in this case we are taking each node represents a city, and there is a city name that is mapped with each node. There can be some other properties also, maybe the postal code of the city or the distance of the city or something like that. So what we will do, we can create a different node class, and let us see, if we are given a node class, how we can create the graph data structure using that node class. So that is what we are going to learn in this particular video. So let's start by defining our node. So this node can be a complex object, okay, but for now I'm just assuming this node contains a string name that represents the name of the city, but one information that I will store here is the list of neighbors, okay, the list of neighbors. So if we store this information here, we will not, it will be easy for us to get the information that we used to get from the adjacency list. So let me show you how you can um, take advantage of this property. So what we are saying, we will store a node, and with each node we will also store what its neighbors are, okay. So we are creating a list inside a node object. So this is what we are doing. So now let us see how we can create a graph. So what information does graph need to contain? It should contain what all nodes are there, okay, and also we should be able to refer a node by its name, okay. So if I say Delhi, so I should know where is Delhi, okay. So what we will do, we will maintain a hash map where string is the key and node star is a pointer. So if I say, okay, I want to find the node corresponding to Delhi, maybe this is the node corresponding to Delhi. So I have the key and I have the value that is mapped. I will need the address of this particular node, okay. So this hash map will store uh, the relationship between the keys that are the city names to the node objects, okay. So they will store the address of a node object. So let's see how we can create this unordered map. So we can use an unordered map here where string is the key and node star is the value, and let us just call this map as m. And now what we want to do, we want to insert all these cities inside our graph. So what we can say, we will make a graph constructor. that will accept a list or a vector of cities. So firstly we need to create all these node objects. Okay, then we need to add the neighbors. So I can say for auto city belonging to cities, map of city equals to new node. So if we are initializing my graph, firstly I will need is what all cities are there. So I will need this list: Delhi, London, uh, Paris, New York. So by reading this list, I will create 4 different nodes. And then in the next step, when the user says, okay, let us add edges between these nodes, I will modify those nodes accordingly. So let me show you how you can do that. If I say, okay, let us try to add edge between, let's say, a city X and a city Y. Okay, and let us assume that these are directed edges. So bool undirected equals false. So if this is the case, then I can say, okay, m of x gives me the node object. Okay, I can refer the node object, and inside that object, m of x is a pointer. Okay, so using that, if I'm accessing a property inside this, I need to use the arrow notation in C++. So I can say, okay, neighbors dot pushback y. So if I say, okay, there is an edge from Delhi to London. Okay, if there is an edge from Delhi to London, what I will do, I will refer m of x. So m of x is Delhi. The value is node star, which is an address to this node. So if I know the address to this node, so I can access the neighbors using this arrow notation. So this is the neighbors list, and I can say in neighbors of Delhi I can store London. So this is what I am doing. So m of x dot pushback this thing, and if undirected is true, then the reverse will be also true. So I can say m of y arrow neighbors dot pushback. So that's it. And now what we can do, we can actually create main. So I will just create main quickly. So I have this code ready. I can say I have a list of cities. I initialize my graph with this list of cities, and then I call the add edge function, and finally I can print the adjacency list. So let us write a code to print adjacency list, so that we can visualize uh, this graph. Okay, so what will happen? So firstly we need to know all the cities. So all the cities are stored inside maps. Map stores information in the form of key value pairs. So for every city pair basically means the name of the city, that is a string, and its address, that is node star. Okay, so what we will get from in this city pair, we will have auto city name, that is uh, city pair dot first, and we will also have the address. So I can say the actual node. Okay, so the actual node is going to be uh, city pair dot second, and if you want to dereference it you can, but let us keep the pointer. So this is a node pointer, and what we can do, we can find out the neighbors by doing node arrow neighbors. Okay, so same thing. So we have a pointer to this node now, and we want to print Delhi and its neighbors. So its neighbors are London and Paris. So what we will do, we will say okay, see out whatever neighbor you have, that we are going to print, and after every row we are going to print handle. Okay, so that's it, and let us see if we can get the correct output. for this particular graph. We have so I have included the relevant header files, and now let us run our code. And okay, so one thing I forgot is to print the city here. Okay, so we can print city here, and now let's run our code. So it says Paris is connected with New York. So in our graph we have Delhi, we have London, we have Paris, and we had New York, like this. So Delhi is connected with London and Paris, which is fine. London is not connected with anyone, which is fine, because the edges are directed. So there is no edge which is going from London. New York is connected with London, fine, and Paris is connected with New York, which is fine. So this is how you can also represent your graph. So I hope you really understood this representation as well. It may be useful in some of the problems where the node structure is a complex. Otherwise, you can simply use the notation that we have discussed earlier as well. That's all. Thanks a lot.